students. Today we are starting new chapter, that is chapter 13 from the part 1 book, Magnetic Effects of Electric Current. In the previous chapter, electricity, we were given importance to both theory part as well as numerical problems. In this chapter, we are giving importance only to the theory part, so there are very less or no numerical problems in this chapter. In the last chapter, electricity, we learned about heating effect of electric current. Based on that, scientists gave a statement that electric current carrying wire behaves like a magnet, and that scientist is Hans Christian Ørsted. He is the first person who gave theory about electromagnetism. Based on activity, he gave that electric current carrying wire behaves like a magnet. Let us see what was the interconnection between electricity and magnet through an activity. Here we need to connect circuit by having the devices key, battery, ammeter and a resistor. Then a thick copper wire is connected between the terminal X and Y. The copper wire is kept perpendicular to the plane of the paper. That is, plane of the paper is inserted in between the copper wire, and horizontally place a small compass near the copper wire. Now see the position of its needle. So first thing is we need to observe before passing the current the position of the needle in an compass. Later on, pass the current through the circuit by inserting the key into the plug. Now we need to observe the change in the position of the compass needle. Now let us take a look at this video. The circuit diagram looks like this. Here we have to observe that compass is placed near copper wire, and observe the compass needle now. That is before passing the current. Now pass the current and observe that the position of a needle has been changed. Observe carefully. This activity indicates a magnetic field is created around the conductor when the current flows through it. Thus, electric current carrying wire behaves like a magnet. Hence, we can say that electricity and magnetism are linked to each other. Let us recall what we know about magnet without going in depth. A magnet is a material that produces a field that attracts or repels other such materials like iron, nickel, cobalt, etc. And there are few properties of a magnet. That is, every magnet has two poles, that is north pole and south pole. And we know that similar to charges, like poles repel each other and unlike poles attract each other. And one more property of a magnet is a freely suspended bar magnet aligns itself in north or south position direction. Try to collect more information about magnet. There are different shapes of magnet like a bar magnet, disc magnet, ring magnet, sphere magnet, cylindrical magnet, and there are two types of magnets like permanent magnet and temporary magnet. And the objects or a material which attracts to the magnet, like usually metals are attracted by magnets, and there are some exceptional metals which do not attract to the magnet. Now let us see what is magnetic field and magnetic field lines through an activity. Here in this activity we are using bar magnet. Bar magnet, it is an rectangular object composed of iron having permanent magnetic property. And in this activity we are using iron fillings also. This is nothing but a small pieces of iron. Here we need to take a white paper on drawing board or anything else and place a bar magnet in the center of the sheet. Now we have iron fillings, right? Just sprinkle some iron fillings uniformly around the bar magnet. And now just tap the board or tap the sheet of paper. Now you will observe that the iron fillings arrange themselves in a pattern as shown in this figure. Look at this diagram and observe that iron fillings experiences a force and that force makes iron fillings to arrange in a pattern. These are the 2 points which can observe through this activity. Using these 2 points we can easily define what is magnetic field and what is magnetic field lines. We know that when we are connecting Wi-Fi from one phone to another phone or one device to another device, it has a certain distance range, right? Out of that distance it cannot be connected. In the same way, for the magnets, there is a boundary. Only within that boundary it will attract the material. Using that or in such a way, magnetic field can be defined as the region around a magnet where its magnetic influence can be experienced. Or in other words, we can say that the area around a magnet in which there is a magnetic force is called as magnetic field. And see how iron fillings near the magnet are arranged themselves in such a pattern that they are causing some lines. And this pattern of lines are nothing but magnetic field lines. It is defined as the iron fillings around the magnet align themselves in the form of lines. And these form of lines are called as magnetic field lines. Now we saw the pattern of magnetic field lines when we sprinkle the iron fillings on a bar magnet. And there are other ways to obtain magnetic field lines around a bar magnet. So let us see what is other method through an activity. For this experiment, we need to take a bar magnet and compass. Place the magnet on a sheet of white paper fixed on a drawing board or anything else. Mark the boundary of the magnet, that is till where it can reaches the objects. After marking the boundary, we know that compass looks like this, which has a needle, and we will name the ends of the needle. Let us assume that the arrow ended position, we'll call it as North Pole, and the another end we'll call it as South Pole. And the next step is we need to bring the compass towards the pole of magnet, another pole of magnet. Now just observe this part. In this needle, this is north and this pole of the magnet is north. From the property of a magnet, we know that like poles repel and unlike poles attracts, right? The way vice versa on that pole also. The compass is in such a way here south and north, which are unlike poles, they will attract, and this is like poles which will repel. So what happens to the direction of needle in the compass? The next step, when we bring that compass next to the one end of the poles, we will get exact position of the needle. That is, unlike poles will attract, that will get south towards the north, and in the side, this side south and north, that's unlike poles attracts, and the direction we will get in this way. So here don't forget that this arrow ended indicates north and another end indicates south. Now I just showed you two spots in the boundary of the magnet. Now we need to repeat this procedure in all over the spots around the bar magnet. Let us see what happens when we take compass all over the spots through the boundary of the magnet. In this way, try to mark the position of a needle using compass and proceed step by step till you reach from south pole end to north pole end. Later on, observe how we got the position of the direction of those needle arrow marks and try to join the points which we were marked in a paper and roughly draw them like a smooth curve, and this smooth curve represents a field line. Repeat the above procedure and draw as many lines as you can see. You will get a pattern shown like in this picture. Through this activity, we can list out the characteristics of magnetic field lines. While you are understanding these characteristics, refer this diagram. Interconnect the points with this diagram. You can understand easily. See, the first point is field line arises from north pole and ends into south pole. Just now in this activity, we placed a compass and draw the direction of the magnetic field line, right? So by looking at the diagram, we can figure out that field lines arises from north pole and end into south pole, right? And when we draw the direction of these marked points from the compass, we saw that field lines are closed curves which result in the formation of continuous or running closed loops. That is our second point. Field lines are arranged themselves in a continuous closed loops. And I'll just explain you the last point. See, the first point what we saw, field lines arises from north pole and end into south pole. This is outside the magnet. What happens inside the magnet? Direction of field lines inside the magnet is opposite to the outside. That is, it arises from south pole to north pole. Look at this diagram. We can easily figure out that the magnetic lines are inside the magnet. The magnetic lines are passing from south pole to north pole. Now, field lines are closer in stronger magnetic field. Now look at this diagram. Find out that where are the field lines are closer. We can observe that field lines are closer towards the end of its poles, that is north pole and south pole. So wherever the field lines are closer, there will be stronger magnetic field. And see the next point. The tangent to the field line at any given point indicates the direction of magnetic field at that point. Now look at this diagram. We have point on one of the magnetic field line and we need to draw a tangent line that, and that tangent line will show that the field line is moving in such a way direction. Look at this picture. It shows that the movement or the direction of field line towards this direction. And see the next point. Magnetic field never intersect each other. Observe this diagram and see what happens to the magnetic field lines when they formed with two different bar magnets. The lines do not intersect each other. Why? Because as for two lines intersect, there must be two north directions, which is not possible. Therefore, magnetic field lines never intersect each other. See, this point they may ask you for give reason why magnetic field never intersect each other. So you need to state that if they intersect, there must be two north direction or two south direction, which is not possible because in compass we have only a needle which has two ends, that is south and north. It not shows at a time a same direction. And the next point is, see, direction of field lines inside the magnet is from S to N, which we studied earlier. And there is one more point, it's not here. They may ask you, magnetic field is vector quantity. Why? That is because magnetic field has both direction and magnitude. And the one more point is, the relative strength of magnetic field is shown by degree of closeness of field lines. Look at this, closeness of field lines. That is nothing but closer or denser the magnetic field lines. If there will be a closer field lines, then they will be greater the magnetic field strength. So where we can observe closer magnetic field lines? Near the poles. Near the north and south poles we can observe more or denser or closer magnetic field lines. So wherever we will find denser or closer magnetic field lines, there the magnetic field strength will be greater. Here in this point we can observe that they may be asked you 1 marks question. For example, the relative strength of magnetic field is given by what? You need to tell either in your own words by statement, or else if they ask you, just fill in the words type. You need to tell degree of closeness of field lines. There is one in-text question here. Why does a compass needle get deflected when brought near a bar magnet? In the third activity, we observed this kind of experiment. The needle of compass is nothing but a small bar magnet, right, which has two ends. One is north and another one is south. When it is brought closer to the bar magnet, its magnetic field line interact with the bar magnet. So the main point which we need to remember here, the interaction between that needle and bar magnet takes place. Therefore, compass needle shows a deflection when brought near the bar magnet. Students, watch the video again and again. Make sure you are understanding the concept. After understanding the concept, write on the notes.